day, friends, and welcome to another great day. I promise you another wonderful online experience today. My name is Philip, your instructor. And please, if you have not subscribed for our channel, kindly do that for us. We need your subscription to keep this program going. For you to be able to do this, just tap the subscribe button below this video. We truly appreciate you for doing this for us. Let's look at our activity for the day. We would continue with bearings and vectors. We are on part 6 of bearings and vectors. And on part 6, we would focus on the following topics. 1. We would look at position vectors. 2. We would express two given points as a column vector. Then 3. We would look at resultant vectors. I guess we have to start now. Position vectors. Now, I believe we all know how to plot points on graphs. And if we are given the point b equals to 3, 2, we would be able to plot it on the graph. Alright, let's try and plot the point b equals to 3, 2 on the graph. So first we would have to draw our xy plane or our Cartesian plane. As you can see from the point b, its x-coordinate is the number 3. So on the x-axis, let's label it to the number 3. Also, the y-axis will be labeled to the number 2 because the y-coordinate of the point B is 2. I believe we still remember that the point of intersection of the y and the x-axis is the point 0, and it is represented by the letter O, that is the origin. So let's show that at that point. Now, to arrive at the point B, we first have to move 3 units on the x-axis because the x-coordinate is 3. So let's quickly move 3 units on the x-axis. We will then move 2 units on the y-axis. So we are now at our destination point. So we are going to put the point B at that particular location. Now it is very important for us to note that the point B is not a vector. It is just a point. In fact, it is an example of a scalar quantity. And the reason is that it doesn't have any direction. You can't see any arrow that tells us where this point B is moving to. However, we can calculate its magnitude. So the fact that a point B doesn't have a direction but has a magnitude tells us that it is a scalar quantity. It is not a vector quantity. But another thing I'll need us to pay attention to is this. Although the point B is not a vector, we can actually locate its position relative to the position of the origin, the 0. So if I ask you to use an arrow diagram or a ray diagram to locate the position of the point B relative to the origin. Which arrow diagram? How will you draw this arrow diagram? Let's draw it and see. So this is what we are going to draw. So like we've already said, the point B itself is never a vector because it does not have a direction. However, the position of the point B relative to the origin O can be seen to be a vector. The diagram on the screen clearly shows that. What this means is that the point B has a position vector called OB. So if we are asked to write the vector OB, which is the position vector of the point B, what would it look like? What would be its S component and what would be its Y component? Well, it would look like this. And as you can see, nothing changed, especially the numbers, the X and the Y component, they never changed. The only thing that changed was that the point B became a vector, which is the position vector OB, and it was also written in column form 3, 2 instead of in coordinate form. Those are the only two things that changed. So now I'll need you to remember this, that all points have position vectors. So for example, if you plot the point C on a graph sheet or on a graph, its position vector is OC. If you plot the point A on the graph, its position vector will be OA. And if you plot the point K on the graph, its position vector will be OK. We'll be looking at some examples whilst we move on. So, but I'll need you to remember this. The other thing I'll need you to remember is this. Sometimes, instead of writing, let's say, OB to represent the position vector of the point B, we would rather use a small letter to represent it. So you will not say OB, but you rather say B. And remember, the B is a small letter. And that will be another way of representing the position vector OB. What this means is that the position vector OK can be represented by the small letter K, and the position vector OA can be represented by the small letter A. The position vector OM can be represented by the small letter M. So we'll be looking at a few examples. So now let's look at these 2 points. The point E and the point K. And please, I'll need you to remember that points are written differently from vectors. Vectors are written in column form, whilst points are written in coordinate form, like it has been done here. We want to plot these points on the number plane. So let's first draw our number plane. Let's show our point of origin. We would then plot the point E, which is 3, 2. Again, we'll plot the point K, which is 2, negative 2. Now, let's show the position vector of the point E with an arrow diagram. So, that is the position vector of the point E using an arrow diagram. Again, I would want us to write the point E as a position vector. And this will be the position vector of the point E. It can also be written as this. At this point, I believe we can all write points as position vectors. So let's try that of the point K. We are going to write it as a position vector. The position vector of the point K can be represented by this arrow diagram. We are moving from the origin O to the point K. So we would write the position vector as this, or this. So now that you can write points in position vector forms, let's look at a few examples. Examples. Write the following points as position vectors. When we write the point M, which is equals to 2, -2 as a position vector, it will become vector OM equals to 2, -2. This is the same as the vector small m equals to 2, -2. Example 2. When we write the point N equals to 3, 4 into a position vector, it would become vector ON equals to 3, 4. This is also the same as vector N, that small n, equals to 3, 4. Example 3. If we write the point P equals to 6, 7 into a position vector, it would become vector OP equals to 6, 7. This can also be written as the vector small p equals to 6, 7. Question 4. The point Q equals to 13, 2 can be written as a position vector as vector OQ equals to 13, 2. This is the same as vector small q equals to 13, 2. I hope you found that easy. Let's look at the inverse of position vectors. Inverse of position vectors. In part 5 of bearings and vectors, we look at inverse of vectors. And I remember very well that we use the word opposite as a synonym of the inverse of vectors. Now, whatever we learned in inverse or opposite of vectors also applies here. Remember, position vectors are normal vectors. The only difference between them and normal vectors is that they begin from the origin, but they are normal vectors. So what we would simply do is to remind ourselves of what we learned in inverse of vectors. So when we take the vector AB equals to 3, 4, its inverse or opposite would be negative AB. Or if we do not want to use the negative sign, then we would have to flip the vector to BA without the negative sign. This is the same as negative of the vector 3, 4. And this will give us the vector negative 3, negative 4. I hope you remember this concept. We are going to apply exactly the same thing in inverse of position vectors. Let's take example 1. The vector or the position vector OK equals to negative 3, 2. We want to find its opposite or inverse. From what we have learned so far, its inverse or opposite would either be negative of the vector OK or the vector KO. That is, if we do not want to use the negative sign. This will give us the negative of the vector negative 3, 2, which would also be the same as the vector 3, negative 2. Let's take example 2. The vector or the position vector ON equals to negative 1, negative 7. The opposite of this vector would be the negative of the vector ON, or just flip it to get vector NO, so that you would get rid of the negative sign. This would give us the negative of the vector negative 1, negative 7, which is the same as the vector 1, 7. So that is how you find the opposite or the inverse of position vectors. But I need you to remember that we are not learning this in isolation. In our next slide, we will be building on this concept to learn another concept. So let's move on to the next slide. Expressing 2 points as a column vector. Now let's first draw the XY plane or the Cartesian plane. Let's show the origin of this plane. Now let's plot the point G with coordinate 3, 3 on this plane. Let's plot another point A with the coordinate 5, 2. Very well, so we have been able to plot the 2 points G with coordinate 3, 3 and A with coordinates 5, 2. Remember, these are points. They are scalars. They are not vectors yet. Now, if I ask you to use an arrow diagram to show the vector GA, how will you do this? Let me give you a clue. The vector GA begins from the point G and ends on the point A. So how will you do this? Using an arrow diagram. Well, this will be the vector GA. Remember, The vector GA begins from G and ends on A. That's the vector GA. Now let's assume that the point G represents a certain town and the point A also represents another town. What it means is that a vector GA will tell us the direction we have to move on to the town A when we are coming from the town G, right? But the question is this: if I'm standing at town G and I'm going to town A, is that the only road I can use to town A? That is the blue arrow. Is that the only road I can use to town A? Think about it. Can there be any other way by which we can get to town A from town G without passing through the blue arrow? Actually, there is another route. Think about position vectors. You can get your clue from position vectors. There is another route or another road by which we can get to town A from town G without using the blue road. Well, the second road you can use is this. If you are going to town A from town G, you can first go back to the origin from town G. And please watch the direction of the arrow. We are moving from the town G, we are going back to the origin. Then from the origin, we can go to town A. So we have come up with two ways by which we can go to town A when we are standing at town G. The first way or the first road is by moving straight from town G to town A. You follow the blue road. The second way is by using the red road. You move from the town G, you go to the origin, then you move from the origin, then you come back to the town A. So that's the second road. So those are two ways by which you can move from G to A. Now, since the two roads will lead to the same place, we can say that the two roads are the same because they will lead us to the same place. The only difference is that one is longer than the other. We are going to come up with a mathematical expression from what we have just done. Just note that the two roads are the same because they will lead to the same destination. So this is what we are going to do. We would state the vector that represents the first road, the blue road. And that vector is vector GA. Now we said that this road is the same as the first road because they will lead to the same destination. So let's bring equal sign or our equal sign. We would then equate it to the second road because the two roads are the same. Now the second road is divided into two parts. The first part, there is a movement from the point G to the origin O. So let's first show that. So from G O, when we got to the point O, then we added another movement or another journey. So we moved again from O to A. So now there is now a movement from O to A. So that will be plus OA. So we have been able to come up with an important expression. And this expression states that vector GA is equals to vector GO plus vector OA. We would very soon be coming up with a trick that would help us come up with expressions like this without necessarily drawing the diagram we've just done. The diagram is just to help us understand the concept, but very soon we'll learn how to do this without using the diagram. So let's move on. Now let's go back to the drawing. The drawing, we have the point G. We've learned how to come up with position vectors when a point is given. So if I ask you to give me the position vector of the point G, what would you say? Well, the position vector of the point G will be the vector OG, and its vector is 3, 3. What if you are asked to write the position vector of the point A? Well, the position vector of the point A will be the vector OA equals to 5, 2. At this point, let's go back to the relationship we established, which is the vector GA equals to the vector GO plus the vector OA. What can you say about these vectors, especially those with O inside them? Clearly, you would see that the GO is an opposite of the position vector OG, whilst the OA is the position vector of the point A. Can you see that? Now, if you can see that, then this is what we are going to do. The GO is the same as negative OG. So instead of writing GO, we would make it negative OG, then plus our position vector OA. Nothing has changed. So what this means is that our vector GA is now equals to negative of the vector OG plus the vector OA. From the diagram, we know the value of the vector OG, which is the position vector of the point G, and we also know the position vector of the point A. So all we need to do is to substitute them into the equation so we can find the vector GA. So can we do that now? The vector OG is 3, 3. So our negative OG would be negative of the vector 3, 3. Let's write our plus sign, and from the diagram, our vector OA, or the position vector OA, is 5, 2. So we are just going to substitute it into the place where OA should be. So the vector GA would give us the vector negative 3, negative 3, plus the vector 5, 2. At this point, we only apply our understanding of how to add vectors. We've already done this, so we just add the two vectors together to get the vector GA. So when we do that, remember the x component would add first, then the y component would also add. When you do that, you would get the vector 2, negative 1. Now at this moment, I'm going to show you a trick on how you can come up with this vector expression without necessarily drawing this diagram. And it's quick, fast, so you'll be able to solve your problems faster. So let's look at that on the next slide. So like we have said, we are going to break up or resolve a vector into its component position vectors. We are going to use the following examples to do that. So we are going to look at these 4 examples. Example 1, we have the vector kn. Example 2, we have the vector fd. Example 3, we have the vector ej. And example 4, we have the vector ef. By the time you are done with all of these 4, you should appreciate how we can resolve these vectors into its component position vectors. Let's start with example 1. The vector kn. 2 main position vectors come together to form the vector kn. To resolve the vector kn into these 2 main position vectors, all we have to do is to start from the point K and move to the origin. So our first movement will be from K to the origin. That vector is vector KO. So we are at this point at the origin. What it means is that we will move from the origin to the point N. So we have to add the vector ON, moving from O to N. So that is how we can resolve the vector Kn into its component position vectors. But let's hold on a minute. We have to adjust this equation a little bit. Let's note that we write position vectors starting from the point O. And all the position vectors we have written so far, we started with the point O. Now, but there's a little problem here. This position vector, KO, started from the point K. It did not start from the point O. So what it means is that we have to look for its equivalent vector that starts from O. What do you think is this vector? Well, the vector KO can also be written as negative OK. OK is the proper way to write position vectors. So that problem has been solved. So all we are going to do is to restate the equation 1 with this negative OK, replacing the KO. So when we do this, we'll get vector Kn equals to negative of the position vector OK plus the position vector On. What this means is that if we know the position vector OK, or even if we know the point K and we know the point N, we can quickly come up with their position vectors and substitute them into this equation or formula and come up with the components of the vector Kn. It's as simple as that. Let's look at the example 2. Example 2. We have the vector Fd and we want to resolve it or break it down into the position vectors that come together to form it. The vector is Fd. So what it means is that we would first start from the point F to the origin O. So that movement is FO. Let's write that first. Then from O, we would move to the point D. So we are moving from the point O to D. So we have to add the vector OD. So that is it. The vector OD is already in its correct form, so we leave it. But the vector FO should be rewritten in the proper way by making the O start. When we do that, we would get negative OF without changing the equation. So we are going to rewrite this whole equation with the negative OF. And when we do that, we would get the vector FD to be equals to negative of the vector OF plus the vector OD. So if we know the point F and the point D, we can easily come up with the position vectors of the point F and of the point D, and we will substitute them into the equation to come up with the value of the vector FD. It's as simple as that, and we'll be looking at that example in our next slide. For example 3, we have the vector EJ. So first we would have to move from the point E to the origin O. That movement is EO. So let's write that down. We would then continue our journey from O to the point J. So we would have to add OJ. The vector EO can be written properly as negative OE. So we will do that, and we will rewrite this whole equation into vector EJ equals to negative of vector OE plus vector OJ. For example 4, we have the vector EF. So we will first start from the point E to the origin. That movement is vector EO. So let's write that first. We would then continue the journey from the origin O to the point F. So that movement is OF. So we would have to add a vector OF. Now the vector EO would have to be properly written as negative OE. And when we do that, we'll get the new equation. Vector EF equals to negative of the vector OE plus the vector OF. It is as simple as that. And I hope you enjoyed this. Now let's come up with a general rule that can help us do this in a much simpler way. Now let's look at the following general rule. If you have the vector AB and you want to write it or resolve it into its component position vectors, you would get this. First, ask yourself where the vector is going to. As you can see, the vector is moving from A and it is going to B. So we would write the position vector of where this vector AB is going to. The vector is going to the point B, so the position vector of the point B is vector OB. So let's write that down. We will then write our minus sign. Finally, we would have to ask ourselves where the vector is coming from. The vector is coming from the point A. So we write the position vector of where the vector is coming from. Since it is coming from the point A, the position vector of the point A is OA. So write the position vector OA. So we have been able to resolve the vector AB into OB minus OA. And please, I need you to note that this general rule is not different from what we have done in previous slides. This vector AB equals to OB minus OA. We've already stated in previous slides that is the same as vector AB equals to vector AO plus vector OB. Again, using this general rule, the vector Kn will be equals to the position vector On, which is the position vector of the point N where we are going to, minus the position vector OK, which is the position vector of the point K where we are coming from. Now let's use what we have just learned to solve some examples. Exercise 1. The question is saying that for the pair of points given, find the column vectors shown. So in this exercise, we have the point G, which is equals to 3, 3, and the point D equals to 2, 1. And we are to find the column vector DG. Okay, so what we will do first is to write the points given to us as position vectors. So the point G will be written as vector OG equals to 3, 3. And the position vector of the point D would be the vector OD equals to 2, 1. Now let's break down or resolve the vector DG into its component position vectors. When we do this, we will get DG to be equals to the position vector OG minus the position vector OD. At this point, all we need to do is to substitute our position vectors into the equation to be able to find the value of our vector DG. So let's do that. So our vector DG is equals to our position vector OG, which is equals to the vector 3, 3, minus our position vector OD, which is equals to the vector 2, 1. When you subtract the vector 2, 1 from the vector 3, 3, you'd get the vector 1, 2. So the vector DG is equals to the vector 1, 2. Let's look at example 2. Example 2. For the pair of points given, find the column vector shown. The point K is negative 7, 1, and the point L is 4, 6, and we are to find the vector KL. So first, let's convert the point K to its position vector. When we do that, we would get the position vector OK equals to negative 7, 1. And when we convert the point L to its position vector, we would get the vector OL equals to 4, 6. Next, we would resolve the vector KL into its component position vectors. So vector KL equals to the vector OL minus the vector OK. I believe we can all do this. At this point, we would have to substitute the position vectors into the vector equation. So our vector KL would be equals to the vector OL, which is the vector 4, 6, minus the vector OK, which is negative 7, 1. When you subtract the vector negative 7, 1 from the vector 4, 6, you would get the vector 11, 5. This means that our vector KL is equals to 11, 5. Let's look at example 3. Example 3. So for this example, we have been given the point P to be 5, 9 and the point U to be 7, 3, and we are to use them to find the vector UP. First, we would convert the point P to its position vector OP, which is equals to 5, 9. Then we would convert the point U, 7, 3 to its position vector, and that will give us vector OU equals to 7, 3. We would then resolve the vector UP to its component position vectors. And when we do this, we would get vector UP to be equals to the position vector OP minus the position vector OU. At this point, we would substitute the position vectors into the vector equation. Our vector UP will be equals to the vector OP, which is equals to the vector 5, 9 minus the vector OU, which is the same as the vector 7, 3. When you subtract the vector 7, 3 from the vector 5, 9, you would get the vector negative 2, 6. This means that our vector UP is equals to negative 2, 6. Let's look at example 4. Example 4. So in this example, we have been given the point K to be negative 8, negative 4, and the point L to be 2, 0. And we are to find the vector KL. So as usual, let's first convert the point K to its position vector OK, and the point L to its position vector OL. When we do this, we would get vector OK to be equals to negative 8, negative 4, and vector OL to be equals to 2, 0. We would then resolve the vector KL into its component position vectors. And when we do this, we would get the vector KL equals to the position vector OL minus the position vector OK. At this point, we would substitute the position vectors into the vector equation. And when we do this, we would get vector KL to be equals to the vector OL, which is -8, -4, minus the vector OK, which is 2, 0. When you subtract the vector 2, 0 from the vector -8, -4, you get the vector 10, 4. Therefore, the vector KL equals to the vector 10, 4. Now that we know how to resolve vectors into their component position vectors, let's look at resultant vectors. So on this slide, we are going to look at resultants of vectors. Let's draw the triangle ABC. Now let's assume that this triangle represents 3 towns: the town A, the town B, and the town C, that are being joined together by 3 straight lines to form this triangle. If I have to move from town A to town B, there are 2 ways by which I can do this. Remember, we did something similar to this when we were looking at position vectors. The same thing would apply here. So if I'm going to town B from the town A, I can move straight from the town A to the town B. That's one of the roads I can use. It's the first road I can use. This road represents a vector movement from point A to the point B. So let's write a vector notation for this movement. So the vector notation will be vector AB, because we move from the point A to the point B. Like we've already said, apart from this road, we can use another road to get to the point B from the point A. So for us to get this, we first need to move from the point A to the point C. We are at the point C, so we would now move from the point C to the point B. So we have 2 roads. The first road is indicated by the red color, which is movement from A to B, and it is represented by the vector AB. And the second road is represented by the blue color, and this movement would have to start from the point A to the point C first. So that movement is vector AC. Then when we get to the point C, we would have to move from that point to the point B. That movement is CB. So that will be represented by the vector CB. Now, because both roads, the red road and the blue road, leads to the same place, point B, what we can say is that they are equal. So we can equate both roads to each other like we did when we were doing position vectors. So let's quickly come up with an equation or a vector equation to represent these 2 roads. We've already shown the first road by the vector AB. So this first road will be equals to the second road. And on the second road, we would first have to move from the point A to C, that is vector AC. So let's write it. Then plus our second movement, which is the movement from the point C to the point B, and this will be represented by the vector CB. So that is how we resolve vectors into components that are not position vectors. And because this resolution leads to the formation of a triangle, usually we refer to it as the triangular law of vectors. Well, this name is just a fancy name. You might not really need it to help you solve your problems, but the most important thing is to be able to resolve vectors into their component vectors. So let's look at some few examples in our next slide. Example 1. For this example, we have been given the vector mg to be equals to 3, 3, and the vector gk to be equals to 2, 1, and we have been asked to find the vector mk. So the first step to take is to find out from the two vectors given to us which point is common to both of them. When you look at the two vectors carefully, mg and gk, the point g is common to both of them. So what we would simply do is to imaginarily put the point g in between the two points m and the point k. Remember, the vector is mk, so in between the point mk is the point g. The vector we are looking for is the vector mk, and we have placed the point g in between the vector mk, or in between the point m and k. So what this means is this: if we are moving from the point m to the point k as shown by the vector, we would first have to move from the point m to the point g. So let's write that. We are now at the point g, so we would have to move from the point g to the point k. So that movement from the point g to k is vector gk. So we would have to add the vector gk to what we have already written. Now from the question, we have been given the value of the vector mg, and we have also been given the value of the vector gk. So all we need to do is to substitute this value into the equation and solve for the value of the vector mk. So let's quickly do that. So the vector mk would be equals to the vector mg, which is 3, 3, plus the vector gk, which is equals to 2, 1. When you add the vector 3, 3 to the vector 2, 1, you would get the vector 5, 4. So our vector mk is equals to 5, 4. Let's look at example 2. Example 2. We have been given the vector hd to be equals to 7, 1, and the vector gd to be equals to 5, 2. And we have been asked to find the vector hg. So our vector hg will be equals to, first let's ask ourselves which point is common to the two vectors given to us. We have the vector hd and the vector gd. So the point D is common to the two vectors. So we would imaginarily put the point D in between the point H and G. What it means is that we would first move from the point H to the point D. So let's write that. And that will be added to, remember we would now move from the point D to the point G. So that will be the vector dg. So it will be added to the vector dg. So our vector hg will be equals to the vector hd, which is 7, 1, plus the vector dg, which is -5, -2. Now, how did we get the vector dg to be -5, -2? Since from the question given to us, there is no vector with -5, -2. Now, the answer is very simple. When you go back to the question, you would realize that we were not given dg, but we were given gd. So if we are looking for dg from gd, all we need to do is to negate the gd to get our dg. It's as simple as that. So that's how come we got the vector -5, -2. Now we would add our two vectors 7, 1 and -5, -2 together. And when we do that, we would get the vector 2, -1. So our vector hg is equals to 2, -1. Let's look at example 3. Example 3. We have the vector cm equals to -8, 4. We also have the vector nc equals to 2, 3. And we are to find the vector mn. So the vector mn will be equals to what? First, we would need to ask ourselves which point is common to the two vectors, the vector cm and the vector nc. Which point is common to them? Well, the point C is common to them. What it means is that we would imaginarily put the point C in between m and n in the vector mn. Next, the vector mn starts with the point m. So we would start from the point m to the point C. So let's write that vector first. Plus, we would then move from the point C to the point N. Remember, the vector ends at the point N. So we would have to add the vector Cn. Now let's note that from the question given to us, we were given the vector Cm. We were not given the vector Mc. So if we have to find the vector Mc from the vector Cm, we know what to do. What it means is that we have to negate the vector Cm to get the vector Mc. Again, we were given the vector Nc. We were not given the vector Cn. So if we have to find the vector Cn from Nc, we have to negate the vector Nc for us to get the vector Cn. So let's bear in mind this information. So the vector mn will be equals to the vector mc, which is 8, -4. So note that the 8 negative 4 was gotten after the negative 8 4 was negated. So just note that. Plus the vector Cn, which is equals to negative 2, negative 3. And in this case also, remember that we got negative 2, negative 3 by negating the vector Nc, which is equals to 2, 3. Because we are looking for the vector Cn. So remember that as well. So at this point we are going to add the two vectors. So when you add a vector 8, negative 4 to the vector negative 2, negative 3, you would get the vector 6, negative 7. Therefore, the vector Mn is equals to 6, negative 7. Let's look at example 4. Example 4. So for example 4, we have the vector hx equals to 2, negative 5. Then we have the vector yh equals to 2 over 3, 4. And we are asked to find the vector xy. Since we are looking for the vector xy, let's write the vector xy equals to down. So we need to determine which point is common to both the vector hx and the vector yh. So it's obvious the point h is common to both vectors. So we would imaginarily write this point in between the x and the y of the vector xy. Now the vector xy starts from the point x. So what it means is that we will start from the point x to the middle point h. So let's write xh. Then plus. So we would at this moment start from the middle point h to the ending point y. So we would have to add the vector hy. So all we need to do at this point is to substitute the vectors xh and hy into the equation so we can get the value of the vector xy. But remember that the question did not give us the vectors xh and hy. Rather, we were given the vectors hx and yh. So all we need to do is to find their opposite to be able to find the values of the vectors xh and hy. So the vector xy will be equals to the vector xh, which is equals to negative 2, 5. Remember that we got this by negating the vector hx, which is 2, negative 5. So I need you to bear this in mind. We then have our plus sign. Then our vector hy, which is equals to negative 2 over 3, negative 4. So at this moment we would have to add the two vectors negative 2, 5 and negative 2 over 3, negative 4. When we do this, we would get the vector negative 8 over 3, 1. Therefore, our vector xy is equals to negative 8 over 3, 1. Well, friends, this brings us to the end of part 6 of bearings and vectors. I would advise you to go to the next video, which is the part 7 of bearings and vectors. And in part 7, we will be looking at the following topics. 1. Finding the angle between two vectors. 2. The midpoint of a line segment. So those are the two main topics we'll be looking at in the part 7 of bearings and vectors. Thank you very much and stay safe. We will meet in my next video, and please subscribe for us if you have not done that. Your subscription is needed for the survival of this program.